What will happen when uniform motion meets accelerated motion? It's going to result in an explosion, I tell you. Okay, I'm just kidding. It's going to result in the so-called projectile motion. It is named as such because it describes a typical trajectory of a projectile launched from a tank, cannon, howitzer gun, or any projectile launcher you can think of. A projectile trajectory is formed from a combination of uniform motion along one dimension, typically the horizontal or x dimension, and accelerated motion along another dimension, which typically is the vertical or y dimension. Why is that so? Because the motion along the vertical axis is affected by gravitational acceleration, the magic number of 9.81 meter per second square we briefly discussed in the last video. The black arrows are the instantaneous velocity vectors of the projectile. These velocity vectors can be resolved along the horizontal components and the vertical components. By the way, I use the term projectile, although it is actually a ball, to befit the trajectory that the ball is undergoing. The horizontal component, which moves uniformly, remains constant, so it moves with the same speed in the same direction throughout the trajectory. Notice how the length and the direction of the blue arrows are uniform throughout. The speed is given by v0 cosine theta, where v0 refers to the initial speed of the projectile when it is just launched or kicked, and theta is the angle at which the projectile is shot. It is technically called elevation angle. So notice that theta should fall between 0 and 90 degrees. The vertical components, which is accelerated or decelerated depending whether the projectile is going up or going down, is shown by the red arrow. Notice how the length of the arrows and the direction at which they are pointing up or down are changing over time. It starts with larger velocity at the bottom when it was just launched, but gravity pulls it down, causing deceleration. The arrows get shorter and shorter until it eventually reaches the maximum height it could reach. And at this point, the practical component of the velocity is 0. And what's left is just the horizontal component, which remains the same throughout. This of course happens just for that split second, because soon the projectile will start going down, pulled by the same gravitational acceleration which caused it to decelerate just now. Lastly, if this whole process is not affected by air resistance, friction, wind, turbulence whatsoever, if gravity is the only force that affects the motion, the trajectory is perfectly symmetrical about the maximum height, about the dash line. It takes the same amount of time for the projectile to reach its maximum height as it does to reach the ground back. In the first half of the motion, the projectile is decelerating because gravity goes against it. In the second half of the motion, the projectile is accelerating because of gravity pull. If the projectile was launched at speed v0, it will hit the ground back at the same speed v0, except that they're off different direction. So I use the term speed but not velocity, same speed but different velocity. Those are quick qualitative analysis of projectile motion. Let us now examine the motion quantitatively. Because projectile motion is a combination of uniform and accelerated motion in two dimensions, it is best that we analyze the motion along its horizontal and vertical components separately. The projectile, or the ball in this case, will launch at elevation angle theta with initial speed v0. First thing first, we need to know how to resolve this velocity. We have done this a couple of times by now, and I don't think I need to elaborate too much. The initial velocity along the horizontal component, which we denote as Vxi, x is used to indicate the resolution of v0 to the horizontal axis, and I stands for initial. Vxi is equal to v0 cosine theta. Similarly, Vyi, which is the initial velocity along vertical axis, is given by v0 sin theta. T seconds later, the projectile is found at coordinate xy, having velocity components Vx and Vy along horizontal and vertical respectively. Notice that these quantities are all function of time. Time is the independent parameters that eventually gel the x and y components of the position and velocity. The horizontal component undergoes uniform motion, which implies that it does not involve any acceleration. So acceleration along x direction is 0. The velocity along x will then remain constant, and that is equal to the resolution of the initial velocity along x, of course. So Vx at any time is equal to v0 cosine theta. The horizontal displacement of the projectile is then given by v0 cosine theta multiplied by t. This equation comes directly from the formula for displacement in uniform motion, which we discussed in lecture 4.2. So far so good. The vertical components undergoes accelerated motion. The acceleration comes by gravity, hence Ay is equal to minus g. Take note of the negative sign in front of g. This negative sign indicates that the acceleration is pointing down because gravity always pulls things down. The velocity and displacement along y-axis will then be given by the equation we just discussed in slide 4 of lecture 4.3. If we then substitute the corresponding expression for acceleration at initial velocity along vertical, we'll have. So notice here that we are not introducing new equations. These are all equations I already introduced and boxed in red in the previous lecture. We are simply applying those equations in the context of projectile motion. By the way, our equation for the vertical displacement is not yet complete, for if you notice, the ball actually is not located at the origin at t0. It is above the origin. Hence, the vertical displacement has to include this initial displacement into the computation. That is the complete answer. Now that is about projectile motion as far as basic concepts are concerned. Before we move on to the next lecture on circular motion, let us ponder on a couple of things. Using those few formulas we discussed in the previous slide, there are tons of questions we are able to address. Some of these questions I will highlight here for us to ponder. We will go through the solution in details during our face-to-face sessions. First, given the initial speed and the elevation angle, what is the maximum height the ball could reach, and how long does it take to reach this height? Second, given the initial speed and the elevation angle, what is the range the ball could reach, and similarly, how long does it take to reach this range? And third, you see that given the same initial speed, the difference in the elevation angle will also affect how far the ball will sail through the air. You shoot too low, the ball will sail for a short while and land close to you. If you shoot too high, the ball will go up really high, spend longer time in the air, but eventually also land close to you. There is actually an optimal angle which maximizes the range the ball could reach. What is this optimal angle? These are the issues we will be discussing in our face-to-face session. Do think about it, find a way to calculate it, and I'm looking forward to your solutions.